All right. First of all, let me say hi. I'm Beej, one of the CS instructors here. You might remember me from such amazing programs as Introduction to Computer Science that we did like 2 weeks ago. But this is the first class that you guys have had, so I'm looking forward to it. This class, Algorithms and Data Structures, is, I'm pretty certain, the absolute hardest sprint in Lambda School. Kind of by a fair amount. So just setting some expectations there, and I hope you don't let that color your impression of me as an instructor too much. I remember, Beej, it was that algorithms week. It was incredibly tough. Yeah, maybe, but I'll be back later with stuff that's less tough. But I do want to talk about the toughness of this week and what's important this week. The reason it's so tough is because the algorithms we talk about, especially in the first 2 days, the data structures for Wednesday, Thursday, are not nearly as hard. The first 2 days of this week are the big ones. These problems are really difficult to think about and reason about and solve. And sometimes people, when it comes to a complicated algorithm to solve a problem, they might work on it for a day or a week or a month or years. Maybe people might work on an algorithm to try to get something that performs well. So the answers to these questions aren't obvious. What's more important to me than you getting the answers for the algorithms problems is that you try really hard to get the answer for them. It's kind of like we're going to ask you to run a 4-hour marathon here, and maybe you work really hard and you run it in 4.5 hours. That's still not shabby. 4.5-hour marathon, not bad. You didn't hit the 4 hours, but you know what? You worked hard at it. You're that much better for it. And that's what's important to me for this week. These mountains that we're going to try to climb, these problems with algorithms, they'll still be there. Even if you don't get the answer in the first 2 days, you can always come back later and attack them again. The sprint challenge itself at the end of the week is more data structures oriented and less algorithms oriented. So I'm not saying that's you're getting off the hook for studying algorithms the first 2 days or anything like that. But if you work hard the first 2 days, but you don't solve many of the problems, then you're still going to be okay. It's the working hard that's important. That's the bit that stretches your brain. I've got an anecdote along these lines. When I want to get challenged in this way, I go to a book called The Structure and Interpretation of Computer Programs. It's also called SICP for short. And you can get it for free online. And you can attack these problems yourself if you want. Some of the problems are really, really tough. And I love the really tough ones. If they're too easy, then I'm like, okay, well, I don't know. It's like the Princess Bride. Inigo Montoya likes to sword fight with his left hand because it's too easy if he sword fights with his right hand, right? So I love the more challenging ones. And in this book, I would go tackle the problems. I'm just going down them, next exercise. And I gave myself a 6-hour time limit on each problem. Wouldn't do it all in one go. Sometimes I'd spread it out over a few days. But if I worked on it for more than 6 hours, I punted. I'm like, okay, I just didn't get this one. And it's a famous book, so the answers are all over the internet. Go look up the answer and see what it's like. But the fact that I had worked so hard that I had spent 6 hours pushing towards that answer meant that when I saw the answer inside my brain, it sat really nicely. I'm like, oh, okay, now I see how to do that. As soon as it was like somebody turned on the light at that moment. And if I had just gone and looked at the answer directly without struggling on it for 6 hours ahead of time, then it wouldn't have made nearly as much sense as it did, and I wouldn't have learned as much stuff along the way. So again, my point is that it's the struggle against the problem that's important here. That you attack the problem really hard and full force and think about it from different angles. What would I try now? This approach isn't working. How can I reason about this thing in a different way? It's like a big puzzle. They're going to be like riddles. You're like, how am I going to solve this riddle? What is the solution for this thing? For the exercises in the repo this week, the solutions are all between like 10 and 20 lines long. They're not long. You can write 2 lines a minute. It'll be done in 5 or 10 minutes. But figuring out what those lines are, that's the brutal part. In one of those SICP problems, I was a part of a line away from the answer. I'd written every line of the program. I knew what I had to fix on this one line. I knew it was at the end of this one line. It was probably like 10 characters I had to write. And I timed out. I got to my 6 hours. I couldn't figure out what those characters were that I had to write on that line. I remember being kind of amazed that I knew how big the program was going to be when it was done. And I just couldn't make it happen. The answer did not occur to me. But it was fun. Don't forget to have fun. I prefer that if you started getting frustrated, that you stop and take a deep breath and remember that it's the challenge, it's the process that's important. And as long as you're on the challenge and attacking it, then you're doing good. And of course, everybody is always around to answer questions. I haven't actually taught this iteration of this. The curriculum's changed since I taught it last. So a couple nights ago, I went and looked at the problems and went, holy cow, I have to remember how to do all this stuff. But I went through them and I'm like, oh yeah, okay, this makes sense and this makes sense. And it comes back to you. I don't know. What's everybody think? Oh, great. Adrian, thank you. Link to SICP. All those are written in a language called Lisp. It's a pretty gentle introduction to Lisp, or maybe it's Scheme. I can't remember. Scheme is a Lisp dialect. Yeah, Scheme. It's a functional programming language. Even learning that in itself will bend your brain a little bit. And anything that bends your brain is good. Means you're learning something. Anytime something isn't quite as you expect, or harder than you expect, or not obvious, that's a learning opportunity right there. I guess for me personally, anytime a day goes perfectly according to plan and nothing is a surprise, I'm a little disappointed. What makes me the happiest is when somebody introduces me to something that I didn't know, that's been hidden in plain sight right in front of me for years. Like, how could I have not known that? But today I learned that. Thoughts on it? Don't forget to have fun. It's going to be really hard. It's expected to be hard. Most important part is the challenge. Nobody's going to die. So you're here at the safety of Lambda School. Like, really, the worst thing that's going to happen is not too bad. As far as I know, no one has died at Lambda School from algorithms. Yeah, Scheme is really different. It's we say it's a different programming paradigm. It's a functional programming paradigm. For me, learning different languages isn't that big a deal as long as they're within a paradigm I already know. So learning new object-oriented languages, no big deal. I know object-oriented paradigm. I can learn object-oriented languages. The first time I learned something about functional programming, whew, man, it's like I had to reason about problems in a completely different way. That was good stuff. Plus, Scheme is really simple as a language, so you can get Scheme interpreters for like your phone. So you can be sitting around waiting for the train or something and writing programs in Scheme on your phone. See how they work. When I was caving with a group of people in California, they would joke around that their cave trips had an 80% body recovery rate. Morbid group of people, man. But no, it's going to be fine. It's just algorithms. All right. Any questions before I start launching into a kind of a lecture in earnest here? I guess I should say Monday is off. We all know this. This is why we're doing this crazy thing on Friday. So I'm going to do this for about an hour, kind of warm your brains up to the concept. Maybe we'll do some recursion or something. And then I say maybe we'll do some recursion or something, like I'm making it up. But no, I have a plan. And then I've got some pre-class videos for you that normally you would have watched before the first class, but just scheduling wise, it makes more sense to give them to you so you can, I think they're all pretty short and you can kind of take them in at your leisure over the weekend or through the rest of Friday, whichever you want. And then Tuesday morning, instead of code challenge, we're just going to launch right into it. So there won't be a coding challenge in the morning that day. It'll just be, let's go with algorithms. And Tuesday will be the last algorithms day. And Wednesday and Thursday, we'll do some data structures, binary search trees and stuff. And then sprint challenge on Friday. And that'll be an intense week. Questions? Oh, you mean after algorithms? I am teaching algorithms. And then I don't remember what's next. Wait, isn't it? It's holiday next, right? And then something. We don't always have the schedule planned out super far, but Tuesday to Thursday will be me, yeah. It looks like me, Sean is getting married, in case he didn't say, but he's going to be on honeymoon after Thanksgiving, so your next week's currently, although this is always subject to change, look like me for algorithms data structures, Thanksgiving break, then Brady for graphs, Brady for intro to Django, and then it's your project week. And then it's winter break for 3 weeks. Ooh. After that, we don't have anything else planned out. Okay, let's see what we got going on here. I'm going to drop you a link to the repo right now. There are going to be 2 different repos this week, one for the first 2 days, one for the second 2 days. That is my understanding, that winter break is 3 weeks, and I'm only slightly authoritative on that. So if you've heard otherwise from somebody else, you might want to get more verification. What was the reply there? Oh yeah, the hackathon. The hackathon's fun. You should do the hackathon. It's intense and fun. You just like sit down and program, and then it's done. No, sorry. By labs, I automatically transcribe that in my head to the project. It's not labs. Your labs is, yeah, that's a rush. Woo! I should defer all scheduling comments to Brian about labs. But I've got that down for February 11th. Oh yeah, I'm going to go through it right now. I'll share my screen. And you should definitely read through it as well. Let's see, where is that thing? Sprint challenge, this, algorithms. 1 second. Hooray! All right. So I'm going to do some demo code today. I guess we'll do some, like I said, we'll do some recursive stuff because a bunch of these algorithms have recursive solutions and it's kind of convenient to think about them from a recursive standpoint. So, I'm not sure what's going to happen at the hackathon. Ryan Hamlin's working on it right now, so he has something in mind, and I'm not sure what it is. But yeah, I kind of like that. I think oftentimes you think of what you want to do, and then you do it. But sometimes it's more like a challenge where everybody does the same thing. But I'll leave that to Brian because he knows all the details. But in this repo, there's a bunch of stuff. There are a bunch of subdirectories here with code to be filled out. There's down at the bottom, there's a suggested order for doing this. The knapsack problem is the hardest. I love it the most. It's a great, great problem that talks about all kinds of dynamic programming and complexity, and it's all kinds of fun, but tough. The rest of these aren't any walk in the park either, though. So, but this is the suggested order for doing them. And so in each of the subdirectories up here, like stock prices, there is a bit of instruction and how to test the program here as well. There's a tester right here. So this test program shows some sample runs. It's going to call this find max profit call over and over again and make sure that results are coming out right. And then in here is just the skeleton. So this function is the one that you'd be implementing to solve this problem. And all the problems are kind of similar to this. So again, you have through Tuesday to work on this part of the sprint. If I were in your shoes, what would probably end up happening is I would read the problem and then I'd walk away from it and it would be sitting there in my brain. I'd be like, how am I going to do this? How am I going to do this? These algorithmic problems probably going to be like 90% thinking about the problem and 10% coding the problem. Figuring out what to code is the biggest deal. So let's see, quick run through. I should have a line of clarification here, but the idea with stock prices is that, let's say a stock fluctuates throughout the course of the day. So it starts low, rises up a little bit, drops a little bit. Let's say I gave you an array that showed the stock prices sampled throughout the course of the day, like this one right here. So these are kind of nuts for fluctuations, but let's say this was Amazon stock, and at the beginning of the day it opened at 1050, and then it dropped to 270, and it rose to 1540, rose to 3800, dropped to 2. The question is, as the day progresses, when should I buy, or when should I have bought it, and when should I have sold in order to make the maximum profit? So I'm going to do one buy, I'm going to follow that by one sell, and out of these prices, which one should I have bought at? And then subsequently, which one should I have sold at in order to make the highest amount of money? So that's the problem. And the answer is probably not obvious. It's designed to be not obvious. Cisco asked this. Man, that's a tough interview question. But these are the kind of questions we're looking at for these first couple days. And so when I attack these personally, I'm like, well, if I forget if I were a computer or not, let's say I'm a human, let me just look through this. Like, how would I figure out? I got to buy one of these, and then after that, I have to sell. So I got to buy at one price. So maybe I buy at 1050 and sell at 270. That seems like a bad idea, because you want to buy low and sell high to make the most money. So, like, okay, maybe I buy at 270, and then I sell at 3,800. That doesn't sound too bad, right? And looking through there as a human, I don't really see any other combination that gets me more money throughout the course of this day. These times of day go forward only, right? It's not like we can buy at 2 and then sell at 3,800, because 3,800 is already come and gone by then. So okay, let's buy at 270 and sell at 3,800. That seems to be about maximum profit, which is 3,800 minus 270. Assuming I just did one share. And so that should be 3530, like this says. So now we need to come up with an algorithm for doing that. And how would we think about this? I don't know. This is just a preview. So I'll let you guys mull that over. Like I said, this week the big challenge is figuring that stuff out. And coding it up is secondary for these first couple of days. For data structures for the second half of the week, we'll be coding stuff up. That's important. But here, just think of it as problem solving. And in a lot of these, I can add, there is a slow way and a faster way to do it. Sometimes the slowest ways, we call it the naive approach. That's not necessarily a cut. That just means the first thing that came to mind was, this is how you can solve it. And so in a lot of these problems, the first thing that comes to mind is, oh, let's just try every combination and then choose the one that comes out right. But sometimes every combination is a lot of things to try, and there's often a shortcut to get you past trying every combination. Every combination thing works. As we'll see, sometimes it doesn't work before the universe ends, but it will work. And if you get there and you want further challenge, you should think, can I make this happen faster? Can I come up with an algorithm that solves this in less time? Or as you'll see with Knapsack, if you get that far, can I come up with an algorithm that solves it in less time, even if it's not quite as accurate? So there's stock prices. What was next? Recipe batches. The idea with this is that you've got in your pantry a whole bunch of ingredients, and then I give you a recipe for like chocolate chip cookies, and then I say, how many batches of this chocolate chip cookie recipe can you make with those ingredients that are on your shelf? So maybe you've got 37 tons of flour, but you only have 4 eggs. So, okay, I can only make 2 batches of cookies, because cookies take 2 eggs per batch. I've only got 4 eggs. Even though I have 37 tons of flour, that doesn't do me any good. So this program is designed to figure that out. You give it a recipe, you give it how much is on your shelf, and it's supposed to tell you how much you can make. So in this case, this should return 0 because we don't have enough butter. It says the recipe takes 100 units of milk. Holy cow. 50 units of butter and 5 units of flour. Man, what is that? What is that much milk, that much butter, and that much flour? Like the world's most unhealthy milkshake ever. I'm going to have to talk to Sean about this, because I'm pretty sure he made this recipe up. Anyway, this is the recipe. This is what you have on your shelf. You've got plenty of milk, 138 milk. You've only got 48 butter. And even though you have plenty of milk and flour, you don't have enough butter. So you can make 0 batches of that recipe. So this is one of those ones where the naive solution might occur to you quickly, but there is actually a clever, faster solution for figuring this out. If you get a solution at all, then that's great. Again, you can stop and ask yourself, okay, that's a solution that works. Can I make one faster? Recipe batches. No, let's see. Some of these become progressively harder and harder. Counting stairs and rock, paper, scissors. These are combinatorial ones. Climbing stairs. So the idea in this challenge is that a child can hop 1, 2, or 3 steps at a time, just like you did when you were a kid. Single step, 2 steps, or 3 steps. And now let's say we give you a staircase with a number of steps on it. Could have a variable number. So the staircase has 12 steps or 40 steps or whatever. We tell you in advance. And the question is, how many different ways are there for the child to ascend the stairs? So the child might be able to do it like 2 steps at a time, or 1 step at a time, then 2 steps at a time, 1 step at a time, 2 steps at a time, or 1 step, 2 steps, 3 steps. There are a bunch of different ways the child could do this. And we want to count the number of ways that we can make that happen. These are good problems. This is the kind of problem that I would have to study before I went to an interview. If I got this cold and I wasn't practiced at it at an Amazon interview, I'd be like, oh man, okay. So how are these being evaluated? I would consider all those things. So there's not we're not grading this part of it. So this isn't like part of your pass evaluation or anything. So when we look at them, the idea is that we want it to be, I would say, let's make it fast primarily. Memory expense is a thing. You know what? I'm going to rephrase that. I don't actually care how fast it is or how much memory it takes. We're going to talk about big O notation here, probably on Tuesday, and it'll be good to consider. We'll talk about how to measure the performance of your algorithm in big O notation and how to make it not only measure the performance, I should say, in terms of speed, but measure the performance in terms of memory consumption. And that's a common trade-off in optimization. Like, okay, we want to make it faster. Let's burn a whole bunch of memory and use that memory in exchange for speed. We'll get some speed out of it. So it would be a totally fine approach to these problems if you manage to get through them all with the first naive solution, then go back and make another pass and be like, how can I make this faster? What can I do to make it faster? Even if it takes up tons of memory. Memory is pretty cheap these days. So this is a combinatorial problem. Counting things. Usually there are recursive solutions to this. Anytime you want permutations, how many different ways are there to arrange 1 hop, 2 hops, 3 hops? How many different ways are there to arrange, let's see, the next question is rock, paper, scissors. And this one is, how many different ways are there to throw games of rock, paper, scissors? So if you're just one player and you decide to have 2 games, how many different ways can we play those 2 games out as this one player? Well, I could throw a rock, then I could throw a rock, or I could throw a rock, then I could throw paper, or I could throw a rock, then I could throw scissors, or I could throw paper, then I could throw a rock, and so on. So this is just giving us all the different ways you could play 2 games. And so for this, if you look in the test program, you'll see these are the results. If we played 0 games, this is all the things we could throw. we played one game, we could do a rock, paper, or scissors. Two games, I could throw rock, then rock, or rock, then paper, and so on. So it's just listing off all these different combinations of these things. So again, when you see things like this, recursive solutions are often helpful. This goes for a while. This kind of growth we'll also study this week. Like, it seems to start out pretty reasonably, you know, this many things, but then suddenly you get up to 5 and it goes forever, right? Have it help us to have it list out 100 games. It's at that point you realize that if I ask this algorithm to print out the possible ways to play out 100 games, it might never finish. There's only so much time left in the universe. How much time do we have left in the universe anyway? 10 billion years, something like that, 15 billion? It's kind of weird to think that you can write a program that would take longer than 15 billion years to complete. But here's one right here. $5 billion for the sun, so the program would have to run in the dark after that. So rock, paper, scissors, combination 1, stock prices. Let's see, making change, is that at last? Yeah. I'm not going to talk about knapsack right now because it's stretch, but similar combination type problem. We want to know how many different ways there are to make change for 10 cents using pennies, nickels, dimes, quarters, and half dollars. So we'll have certain denominations of money, and the question is, for a given number of cents, how many possible different ways are there to hand that out in change? When you decide to go in and pay your $400 at parking tickets in loose change. Anyway, again, it's the thinking about these problems that's the hardest part. And you'll probably want to do a bunch of research and hunt around to help solve them, and ask lots of questions on the help channels. What we'll do is, if you come to the help channel and you're like, okay, I'm stuck on this guy, then our question is, what have you tried? Because we'll want to build off what you've already done to see if we can point you in the right direction. At this point, I would expect people feeling a little bit of trepidation, but hopefully not too much fear. Oh man, that sounds familiar. It was like forklifts full, right? We're just pallets of change. Anyhow, all right. Let's see, 156. Sure, I don't want to keep you guys all afternoon because I know there's stuff that you have to do with PMs. So I'm going to run through some quick stuff here. And some of this stuff isn't going to be might not be entirely obvious to start, but let's do some recursive stuff here. Oh, do I want to do the recursive thing and the stack thing? Sure. All right. So a quick disclaimer and an apology. I have been doing the C portion of the curriculum for weeks, and that means I'm going to totally be rusty on Python, and I'm going to make dumb mistakes because my brain is in C mode. And so please forgive me. And you're like, why did Beach put parentheses there? Why did Beach put semicolons everywhere? Uh, it's not entirely easy to just switch languages, but I'm going to make an effort. So, all right. I'm going to code in Vim here because it's a little faster than VS Code, but let's see if I can make it happen. I saw some typing. Was a question forthcoming? Let you keep typing here while I start typing. So for this, I want to do a quick routine that determines if an array contains a value. Of course, there's already ways to do this in Python, so it's kind of contrived, but or a list, I should say. Sorry. See, I'm already in C mode. It's a list, not an array. So if we want to see if it contains a certain value, if I want to see if it contains number 3, for example, and then I'll pass it a list L and a target value that we want to see if it contains. So if we wanted to write this in a straightforward way, we might just do a loop or something, right? You might do like a for in or something like that. Or actually, there is already an in Python, isn't there? You can just check and return. But I want to write this in a recursive way. Now, pretty much all loops can be written as recursion as well. But let's think about this in a recursive way. So this project is due Tuesday morning, right? So this module with the algorithms, this is a 2-day module. So you have until the end of the day Wednesday, basically. So sorry, end of day Tuesday. Stop myself. You have until end of day Tuesday, not Tuesday morning. Thought about writing an engine to measure the efficiency of the student's algorithm. That would be interesting, but it's probably easier. Well, it's definitely easier for the instructors to just look at the algorithm and be like, "Oh, this is the time complexity of that algorithm." Writing a yeah. Well, hold that thought maybe until Tuesday, because I want to, when we talk about big O notation and figuring out algorithmic efficiency, there are ways that we can actually measure these things. And we'll talk about it then. So one way of thinking about this list contains recursively is, I could say that something like this. I'm going to write some pseudocode here. I could say like the list contains function is sort of defined as, and I'm going to make something up, defined as, saying something like the head of the list the head of the list equals X, or list contains the tail of the list, or remainder of the list, maybe I should say, of X. So what have I written here? I've written this definition of list contains. So I'm saying a list L contains the value X if the head of the list is equal to X, or if the rest of the list has X in it. So the list contains X if the head of the list is X, or if the rest of the list contains X somewhere. This kind of makes sense, right? If the head is X, then it contains X. Or if the remainder of the list, not counting the head, if the rest of the list contains X, then the list also contains X. And that's all well and good, but of course, I've referred to myself in this pseudocode like list contains, its definition actually calls list contains. And that's the recursive part of it. That's why we call it a recursive definition. And so we can use this if we want to and do something very similar. So we'll take our pseudocode. Yes, this is very, very Lispy. Very much like car encoder. If you've done functional programming in Lisp, this is probably quite familiar. So we can take a look at the head of the list. Something like this, list.pop. Oops, there's my semicolon for C. So we can take a look at the list, the head of the list, and we could say if the head is equal to X. See, I'm programming in C. It's so painful to change. If the head is equal to X, then we found it. Otherwise, we want to return what happens. List contains the remainder of the list contains X. And now I've already popped the head off the list. So at this point, the list is its own remainder, right? The list has been shortened now because the head's been removed from it. So I'll say if the rest of the list contains X. So that's pretty much what we've got here. So we can do a quick run through. So if our list has, let's make it 1, 2, 3 to be shorter. We want to check to see if this has 2 in it. We'll start off with, we'll call list contains, I'll just put it right here, 1, 2, 3. We want to know if it has number 2 in it or not. So if we make this call, what happens? We come in here, we look at the head, which is 1. Is the head equal to 2? No, it's not. So we go here, and we're going to return whatever this call returns. So we call in here again with the rest of the list, which now contains 2 and 3. Right? Pop takes off the head of the list in Python, right? I hope so. So the list contains 2 and 3. We pop the head off, which is 2. We say, is the head equal to 2? Then it is. We return true. Great, we're done. We found it. Now, we return true. When we're executing, we return to exactly this point right here, right? Because we called list contains, but we haven't yet returned yet from the first time we called the list contains function. So list contains, the second call from here has returned, and it returned true. So now we are going to return whatever it returned, which was true, which means we're going to return true, which is what we wanted to return because we found it. Whew. Oh. Can you just convert the list into a set and check if the value's there? Totally. Yeah. Yeah, for the record, this is not the right way to do this in Python. This is just a demonstration of doing something recursively and taking a recursive definition where we've defined this problem as, oh, hey, this problem is self-referential, or this problem is each problem is made up of self-similar, smaller problems. So we've defined it as saying, okay, it's the head is it, or the rest of the list is it. And by defining the problem that way, and you're going to do this in these challenges these first couple days, you're going to be like, is there some recursive definition that I can use to define this problem? And especially for things like all those combinations of rock, paper, scissors hands, there are recursive definitions that define these problems. And if you can figure out what that is, and you can write it down kind of like this, then you can translate that into code. There's one thing we haven't done here, though. If I run this program here, does the list 1, 2, 3 contain 4? It doesn't, clearly. But what happens when we run it, we step in here, we pop 1 off the front of the list for the head. That's not 4. We keep going. So we jump in with the rest of the list and try it. We pop 2 off. That's not 4. We keep going. We pop 3 off. That's not 4. We keep going. But now the list is empty. I'm not even sure what happens when you pop off an empty list. What does happen? What does happen? Bleh. Bad things. All right. So yeah, we need some kind of terminating statement. These are called base cases. So something that's going to break us out of the recursion when we have reached the end effectively. And so we can put a base case in here that says if the length of L is equal to 0, that means we got to the end and we didn't find it, right? So I'm going to return false there, saying, hey, we didn't find it. The terminating statement. I don't know, maybe we just need terminating statement. Terminating statement. Happy fun voice. I'm cracking myself up. All right. Y'all ain't laughing though. So I think this probably works. Should I try it? Let's see. So let's just give it a couple tests here. False and true. Is that right? Yeah, 1, 2, 3 does not contain 4. 1, 2, 3 does contain 2. I'd say the most important takeaway here is this bit right here. That if you can find that definition of that function that's self-referential like that, that's awesome. Notice that our definition here, it didn't have our other base case in it. We had to code up another base case that wasn't referred to. It was kind of implicitly implied, redundantly, implicitly implied by the fact that these are true or false. But this right here, coming up with this concept, this is what gave us the framework for writing out that recursive solution. It's kind of elegant in its own little way. I like them. They're like, oh hey, it's thoughts on this thing? Everybody's like, okay, not okay. know it's not quite enough to go on because you haven't really sunk your teeth into it, but I hope that's enough to hint towards some of the solutions a little bit. Probably not. Carlos, it's probably not faster than using a for loop in this case. Again, this is just for demonstration purposes of how to find a recursive definition to a problem, and then take that, if you can find that recursive definition, then take that and translate that into code. But for loop's probably faster. In languages like Lisp, and if you want to branch off to the side, this is not important for this part of the class. There's something called tail call optimization, sometimes just called TCO. Tail call optimization is something that some languages do in order to make recursion, in some cases, just as fast as loops. This particular function could not be optimized in that way, at least not the way I have it written. But yeah, this takes up space. Like every time you make a recursive call, it's got to save all your local variables on the stack, and it does this for every recursive call you make. And notice for this, we're making one recursive call for every element of the loop. So if the loop has 3 elements, it makes 3 recursive calls. If it has a bazillion elements, it makes a bazillion recursive calls. And that takes up more and more space on the stack. Yeah, like I said, if you want to know more, not necessary, but look up tail call optimization. Kind of a neat concept that might actually be coming to JavaScript. Let's do one more example here. I'm gonna go ahead and paste this in for you guys if you just want it for reference. I'm going to do Fibonacci on Tuesday, I think. I was thinking about doing it today, but it's Fibonacci. I love it as an example for dynamic programming, so we'll talk more about that then. But Fibonacci is a great one for recursion. And there are ample opportunities to optimize that. All right, let's do one more with, this one isn't going to be recursion, but oh, this is going to be fun to code off the top of my head. But we're going to make a Python stack, and we're going to kind of do I want to make this class? Sure. All right. It's class, right? Do you capitalize classes in Python? Tell me if I'm making a syntax error in here. So this is just going to be kind of a bare wrapper around here. Push and pop. Make my screen bigger for you guys. Does that look right? Did I mess this up anywhere? Again, apologies. Oh, is it append? Is it append and pop? Does that sound right? That sounds right. Okay, cool. Just a quick test. Thank you for that. JavaScript uses push. More languages you know, the more languages you get mixed up in your brain. All right. So push and pop, we got this stack. I want to know what the largest element is in the stack. Pop seems to be from the end. I pushed 2, or I appended 2 and 3 on. I popped and it took the 3 off. So I think we're good. Just leaving the 2. In my little test, here. Okay, so what's this code going to look like for the largest? I just want to go through the stack and see what's in there. And here again, I'm totally forgetting my Python. For in works here, right? I want to loop through everything. All right. For v in the stack, if I, oops, in the stack, self.stack, we'll go through here and we want to see if it's the biggest, right? So I'm going to do something kind of cheesy here. What's the smallest number in Python? I can't remember how to write the smallest number. We're just going to make a really small number. Oh, it probably does, but that's gonna spoil what I'm about to do. Again, this is going to be for demonstration purposes. So the question is, how long does this take to run? Let me just ask the question that way. In general, if you were going to answer that question in a general way, how long does this take to run? Order in. Yeah, order in. That's what I wanted. How much Big O stuff have you guys done? Okay, just making sure, because I was like, I wasn't expecting order in as the answer. It is order in, but what does that mean? Linear time complexity. What we're getting at there is that the amount of time it takes to perform this loop right here is directly proportional to how big the stack is. So let's say if the stack had 1 item in it, it took 1 unit of time to process that 1 item to do this stuff. If the stack had 10 items, then therefore it would take 10 units of time to do this stuff. So how long this function takes to run is proportional to how big the stack is. And that's okay, maybe. As long as the stack stays small, we're good with it, right? If it takes 1 unit or 3 time units, it doesn't really matter. 1 time unit's pretty small these days, so nobody will notice, right? Good programmers always have this. Yes, it's like looking through every J in the phone book to find Jorgensen. Phone book, whatever that is. So yeah, this might be fine, But all good programmers in the back of their heads, when they're programming this stuff, they think, how long is this going to take if this thing gets really big? And is that a problem or not? Most often it's not a problem. You write a loop and you're like, okay, well, I've written a loop to loop over every character that the user inputted. But I, as a good developer, recognize that this is going to take longer and longer the longer the user input is. And then you stop and you think, is there ever going to be a case where the user input is, say, 400 trillion bytes? And what's going to happen to my program if it is? So good programmers always stop. It's pretty much with every loop, although really honestly, good devs, when in the back of your head, you're like, I just wrote a loop. I know that's an order in process and it's going to remain small. I'm okay. That little thought process happens kind of subconsciously. But when you write more and more complicated things, especially with nested loops, or especially when the numbers get big, then programmers are like, okay, now I really want to analyze this and see what the time complexity is. So let's say that we have this stack going, we've written this and it's been working fine, but then due to a change in business processes, suddenly our stack grows to, say, 300 billion items. We've got 300 billion items in the stack. That is a big stack. And now people are noticing. People are like, you know what, hey, when I click the OK button here, it took like 4 seconds to get back to me. And we're like, okay, well, that's okay, or this must be because we have this thing where the stack, we thought it would have like 30 things in it, but you have 300 billion things in it. So now this largest lookup, this is taking a while. And the client's like, yeah, we need that to come back really fast. So let's see what we can do. What could we do? How could we make this faster? How can we make it faster to find the largest number than looking up things in and looking through all the things? Here's one of those challenges. Can we change this from what we've been calling it here, an order n process, which means linear time? It means if you have n things, it will take a certain amount of time. And if you have n times 2 things, it'll take twice as long. Can we make it faster? What if I said, I want to be able to look up the largest thing in the list in the same amount of time every time, regardless of how many things there are in the list? Could we do something in login time? That's a lot better. We'll talk more about what that means later, but login time definitely way better than n. What about order 1 time? You could keep track of the max as you add it. So something like this, self.max equals -9999. If v is greater than the max, then the max is assigned v. Just going to put semicolons everywhere. Now we're keeping track of the max as we go. That's kind of cool. How about this? That's rather faster. Now our largest doesn't care how big the stack is. Something interesting to note here is that we're still doing all those comparisons. We used to do it in a loop right here where we do it every time. We're still doing those comparisons up here, and we're still keeping track of the max, right? This is exactly the guts of the loop that I used to have down here. If v is greater than big equals v. Now I've got if v is greater than max, max equals v. Sorry, this should be self dot clearly. So I've taken the guts of that loop, I've moved it out of the loop, I put it up here into push. The word we use for this is that we have amortized the cost of keeping track of the max. We've amortized that across the push. So now, instead of when we call largest, we do all those comparisons to see which one's the largest. Now we do one of the comparisons every time we push something new onto the stack. And so we've taken that work and we've kind of spread it out over across all the pushes. And so now when we go to our largest, we just have to return self.max. And that takes the same amount of time to do no matter how big the list is. The number of items in the list, n, could be 1,000,000, 1,000,000,000, 1. Doesn't matter. Returning self.max always takes the same amount of time. We call this an order one process when we get to talk more about big O notation. Again, this is a preview. We'll talk more about that later. But order one is as good as it gets. It means that your algorithm takes the same time to run no matter how big the input data set is. So order one is choice. There's still a flaw in this algorithm, though. Anybody see what it is? Or I shouldn't say a flaw in the algorithm, but a flaw in our stack at this point. We've introduced a flaw that wasn't there before. Okay, our pop. How are we going to deal with that? So if we push on 1, 2, 3, 4, the max is clearly 4. But if we pop the 4 off, 4 is not the max anymore, it's gone. But we don't have a clean way of getting the max right now, the new max. I mean, we could run our old loop inside pop. Oops. But that would make pop into an order n process. So now things get interesting. I don't want to labor this point too much because I know you guys have to go. It's 2:30. But maybe something to consider there. Again, this isn't part of the assignment, but is there some way we could keep track of that max, maybe by using more memory somehow, a different process that we could use? Anyway, I wanted to bring that one up as an example of, hey, sometimes there are ways that you can change your code around. Maybe you move something out of a loop, amortize that across a bunch of other calls that happen, and then get better performance out of your function that computes the largest. All right. Thoughts on that? As you explore these problems, you're going to find new ways of solving things that you hadn't thought of before. So these were a couple examples here of things that you might come across, things you might find useful as you're working on them. I would encourage you to not just look up the answer until you've hit some timeout that you've imposed on yourself. Reading somebody else's answer to these algorithms, while useful, that's worth 10 points. But studying these problems yourself until you've exhausted all possible routes of exploration, that's worth 1,000 points. That is where the learning happens. Orders of magnitude more, absolutely. On that note, PMs are around. I'm going to try to be around as much as I can. Post questions on help, talk amongst yourselves, share ideas on how to solve some of these things. It's definitely challenging stuff. And after this week is done, I'm not going to expect people to be super experts on solving this stuff, but you will have done the first batch. First batch is always the hardest, probably better to get it here at Lambda School than in a job interview, and so on. Oh, as always, I had one more thing I was going to mention that I can't remember, so probably going to have to wait. What was it? Oh, I swear it was something important about bureaucracy. Oh, well, I'll post it if I remember. Are there any PMs here? Have I forgotten something obvious? It's terrible. All right, I'm going to also study these algorithms on the weekend just to make sure I have an absolute handle for better explaining them. Tricky stuff, but fun stuff. All right, gang. Have a good weekend. I will post this video. I'll post the pre-class videos that have way more information in them as well. And again, I'll post the link to the repo. And I'll catch you all on Tuesday.